We know that if anything pulse is 0, it is equal to unity. Then rate equation can also be written as rate is equal to minus dr divided by dt, which is equal to k into 1. Initial state, it shows that the concentration of the R naught, it is nothing but a initial concentration of the reactant will be 0. What does the gas phase reaction indicates? Here both the reactant and the product should be present in the gaseous state. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called Chemical Kinetics. Under that, we discussed about the order of reaction and also we discussed about the molecularity of a reaction. Today, let us move on to the new topic of this unit about the integrated rate equation. So, you are going to learn how to derive an integrated rate equation for the zero order reaction and for a first order reaction. And also, we are going to understand the significance of first order rate equation and we are going to understand the rate constant for the first order gas phase equation. Okay. So, firstly, we'll go directly move on to the integrated rate equation. So, how to derive with the zero order reaction? Let us understand. Already we know that zero order reaction is nothing but a reaction is a one in which rate of the reaction is independent on the molar concentration of the reactant. In case of the zero order reaction, we already understood that the rate of the reaction is independent on the molar concentration of the reactant. So, I can write this as rate is equal to K into molar concentration of the reactant. So, here the rate is not depends upon the molar concentration of the reactant, it is independent. Then only we can say it is a zero order reaction. For this, how to derive the integrated rate equation? Let us understand first. I will consider the reaction where reactant is giving rise to the product. For that, how to write the differential rate equation? Let's see now. Rate is equal to minus dr divided by dt is equal to k into molar concentration of the R naught. Why it is minus? Because already we have understood that during the time 0, the molar concentration of the reactant will be same. But as the time passes, the concentration of the reactant will be started decreasing and the concentration of the product will be started increasing. That is why if I write the rate equation in terms of differential rate equation, it will be become minus, as well as if you write the rate equation, it will become minus for the reactant because their concentration will be, it will be go on decreasing as a time passes. Okay. So, rate is equal to minus dr divided by dt, which is equal to k into R naught. Why it is R naught? Because this is a zero order reaction. We know that if anything pulse is 0, it is equal to unity. Then rate equation can also be written as rate is equal to minus dr divided by dt, which is equal to k into 1. Why this is become 1? Anything or any quantity raised to the power 0, it will be become 1. So that I can directly write this equation by taking dr as an outside. So, dr is equal to minus k into dt because k and dt will be multiplied with each other and you will get minus dt. So, this is how I will get the equation just by rearranging the dr. Okay. So, I have taken out the dr outside, which is equal to minus k into dt. Now, for this equation, I am going to integrate on both the sides. We know that the integration of dr, which is equal to, for the k we are not doing the any integration because it is a constant. Is it right? the integration of dt. We know that the integration of dx is nothing but a x only. Is it right? So you can write directly as the concentration of R or the molar concentration of the R. So minus K into the integration of the dt is nothing but a T plus I. Why it is I? Because this is a integration constant. So this is how I'll get this equation by integrating on the both the side. When I get this equation here, the I represents the integration constant. Now, after getting the integrated rate equation, at a time 0, I'll consider. So, I'll consider time 0, then the concentration of the reactant will be also equal to the molar concentration of the R naught. Why? We know that at the initial step or at the first step, the concentration of the reactant will be as such. It does not decreases or does not increases because it does not involved in the reaction itself at the time 0. So that we can write the molar concentration of the R which is equal to molar concentration of the R naught. Now, by this we can say that R naught, which is nothing but the initial concentrations of the reactant, by substituting the R which is equal to molar concentration of the R naught in the first equation, we will get R naught which is equal to minus K into 0 plus 1. Anything into 0, it will become 0. So now you got that R naught, it is nothing but a I, because K into 0 is a 0 plus I. The I value will be obtained as the molar concentration of R naught. Now I have got the I value or the R naught value. By substituting the values of the I in the first equation, you will get R is equal to minus KT into R naught. Simply by further simplifying this equation, we will get the rate constant. So for this, I'll take out the K outside and R naught minus R divided by T. Simply by, I'm just rearranging the reaction in order to express my equation in terms of rate constant. Okay, that is K. So that is why I have taken out the K outside, R naught is there. The R which comes outside means it will become minus R divided by T. So if you compare this equation to, especially this one, plus the concentration of the R naught, which looks like a straight line equation, that is Y is equal to mx plus C. Here Y is nothing but a concentration of the R and M is nothing but a K and X is nothing but a T and C is nothing but a concentration of R naught. So the equation 2 will be look like a straight line equation, and from this we can say that by plotting the concentration of R versus time, this shows that this is a particular point where the initial concentration of the reactant will be 0. Understood? We are plotting the concentration of the R versus time because it looks like a straight line equation. So at the initial state, it shows that the concentration of the R naught, it is nothing but a initial concentration of the reactant will be 0. Later as the time passes, it will be decreases. If you take the slope for this, you will get the negative slope. This is how we can easily derive an integrated rate equation for the zero order reaction. So if they asked for the 3 marks, you have to derive the entire equation from here to here for the 3 marks. And remember, again, this is very important for the examination point of view. It is very important for the examination point of view, especially for the 3 marks. They can ask this question to derive the integrated rate equation for the first order reaction. Hope you all understood with this derivation. At the last step, if you compare the equation 2 with the straight line, you will understand that the concentration of the R is plotted against to the time. You will see that the initial concentration of the reactant will be 0. As the time passes, it will be go on decreases. If you take the slope, you will get the negative values of the rate constant. And remember, by rearranging this, you will get the rate constant equation. K is equal to R naught minus R divided by T. Now, let's see with the integrated rate equation in terms of first order reaction. Now we have understood that how to derive an integrated rate equation for the zero order. But now we are understanding with the first order reaction. What is the first order? We already know that in the first order reaction, the rate of the reaction is proportional to the first power of the concentration of the reactant. Or you can say that in the first order reaction, the rate is equal to the K into the concentration of the reactant to the power 1. That is, in the first order reaction, the rate of the reaction is directly proportional to the molar concentration of the reactant raised to the power 1. Then only we can say it is a first order reaction. So now I'll consider the simple equation where the reactant is giving rise to the product. Now I'll write the differential rate equation for this. Rate is equal to minus dr divided by dt, which is equal to K into R. We know that if you don't write 1 also, it indicates that it is a first order reaction. Okay. So, or you can write that dr divided by dt, which is equal to K into dt. Here, just I have rearranged the dt with the R and I have written this equation. By integrating on both the side, so for this, if you integrate it, you will get, I'll write integration of d into R divided by dr is equal to K into integration of dt. So, what is the integration of dx divided by dx? It is nothing but a ln R, and it is a K as such. It is nothing but a t plus I. Here we are doing the just integration for this equation, and you will get this a ln R, which is equal to minus kt plus t, and these are minus. Okay, where I represents that it is nothing but a integrated rate constant. So it is a integrated constant. Now after getting this equation 1, by integrating this equation at a time 0, then I'll consider that the concentration of the reactant will be equal to the initial concentration of the reactant at a time 0. Then the entire equation you will get, the concentration of the reactant will be equal to the concentration of the reactant at an initial state. So ln R naught, which is equal to minus K into 0 plus 1, because the time is 0. K into t is 0 plus I. So anything into 0, it is 0. So ln R naught is equal to I. So by substituting the values of the I in the first equation, you will get ln R, which is equal to minus kt plus ln R naught. Here I have taken out the kt outside. So ln R naught minus ln R. So this will be looks like log A minus log B. Log A minus log B, which is nothing but a log A divided by log B. Is it right? That is why I have written K is equal to 1 by T into ln R naught divided by R. Why I have written this? Because this will be looks like a log of A minus B. Okay. So that can be written as log A divided by B. If you have written this equation, we know that here it will be present in the ln. So in order to convert into the log, we need to multiply it with a 2.303. That is why I have written rate constant, which is equal to 2.303 divided by T into log of concentration of the reactant at the initial state divided by concentration of the reactant. This is how you will get the final equation by converting the ln into log by multiplying with the 2.303. This is how the first order rate equation can also be derived by using integrated rate equation. Hope you all understood with this derivation. Again, if they ask you to write for the first order rate equation for the 3 marks, this is also very important for the 3 marks. You have to derive from here to here for the 3 marks, and it is very easy. Only thing is, pause the video, understand it, and repeatedly you do the practice, then you will understand that how to derive the equation. Now let us understand the significance of first order rate equation. Now we are going to understand the significance of the first order rate equation, that is K. So let us consider ln R, which is equal to KT plus ln R naught. By comparing the equation, this will be equal to the straight line equation, that is y is equal to mx plus c. Here we have plotted you can compare this, that is ln R, which is equal to minus KT into ln R naught, with the y is equal to mx plus c. Okay, here you will plot the ln of R versus time. At the initial stage, it shows that ln R naught, it is nothing but the initial concentration of the reactant will be 0. As the time passes, the reactant concentration will be decreases and you will get the slope like this. Next, or you will get a straight line like this, because the concentration of the reactant will be started decreases as the time passes. Now, if you have taken out the slope for this, this shows that a rate constant K, that will get the negative slope. This is how, by using the first order rate equation, you will get the negative values for the K. Now, directly I will consider the second condition, where the first order rate equation will be written as K is equal to 2.303 divided by T into log of the concentration of the reactant at the initial state divided by concentration of the reactant. Now I have taken out the log of R naught divided by R, which is equal to K into T divided by 2.303. Now if we plot the graph of log of R naught divided by R versus time, you will get the straight line like this. This shows that at a particular point or at time 0, the log of concentration of the reactant at the initial state divided by concentration of the reactant, it will be 0. As the time passes, it will started increasing, and if you taken out the slope, you will get the K value as K divided by 2.303. This is how, we can easily understand the significance of the rate constant by understanding with the first order rate equation. Next, at a time t1, this is a third condition. At a time t1 from the equation, we can say that ln R1, which is equal to minus KT1 plus ln R naught. This is a equation 1. And at a time 2, I'm considering ln R2, which is equal to minus K2 plus ln R naught. This is a equation 2, where R1 and R2 are the concentration of the reactant at a time T1 and T2 respectively. Now by subtracting the equation 1 with the 2, so equation, what does the ln R1 is equal to KT1 plus ln R naught. Is it right? So now I'll subtract the equation 2 with the equation 1, so that ln R1 minus ln R2, which is equal to minus KT1 minus of minus KT2. Now minus into minus again plus. So if you taken out the K as outside and the remaining is T2 minus T1. So you will get, again here this will be looks like log of A minus log of B, and that can be written as ln of A divided by B. So ln of R1 divided by R2, which is equal to K into T2 minus T1, because I have taken out the K as the constant. Now I have taken out the K outside. So 1 divided by T2 minus T1 ln R1 divided by R2. Now in order to convert this entire equation in terms of log, I multiplied with the 2.303. You will get K is equal to 2.303 divided by T2 minus T1 log of concentration of the reactant and the concentration of the reactant at a time 2. This is how we can easily understand the significance of the rate constant by using first order rate equation. Hope you all understood with this. Next, we'll see with the rate constant for the first order gas phase reaction. First order gas phase reaction. What does the gas phase reaction indicates? Here, both the reactant and the product should be present in the gaseous state. Understood? Both the reactant and the product must be present in the gaseous state. Then only we can say it is a gas phase reaction. Here, the A is giving rise to B and plus C. Okay, where A is a gaseous state, B and C is also in the gaseous state. Then only we can say it is a gaseous phase reaction. Let us consider the typical first order gas phase reaction. Let Pi be the initial pressure of A and Pt will be the total pressure at time t. Integrate the rate equation of such reaction can be derived as total pressure. We know that Pt is nothing but how many elements are there? 3. So total pressure is obtained by partial pressure of A, partial pressure of B, then partial pressure of C. Pa and Pb and Pc are nothing but a partial pressure of A, B, C respectively. In order to calculate the total pressure, I have taken over the partial pressure of A, B, C. Then, if X atom with the decreasing the pressure of A at a time t, if X atom will be the decreasing in the pressure at a time t, then 1 mole of each B and C is being formed and increasing in the pressure of B and C will be also be X atom each. Here we know that 1 mole of A is giving rise to 1 mole of B and 1 mole of C. The decreasing in the pressure is obtained by X atom and that can be written as Pi is a pressure of the A. Okay. Then this is 0 and again this is 0. Then the decreasing in the pressure that can be obtained by Pi minus X atom and this will be X atom and this will be X atom for the B and C. Then at a time 0, then at a time t, how can we written this equation where Pi is nothing but the initial pressure of the reactant at a time 0, then Pt is equal to Pi minus X plus X give rise to Pi plus X. So here I have taken out the Pi plus X as a common and I have written the X outside. So I have taken out the X outside and I have taken out this Pt minus Pi. Okay. Then we know that X value is nothing but a Pt minus Pi. Pa is equal to P1 minus X and we know that what is the X here? Is it right? P1 minus Pt minus Pi. Now, you know, if you substitute this value, you will get, there are 2 Pi will be there. So, there are 2 P1 minus Pt. Then, K is equal to 2.303 divided by T into log of P1 divided by P2. How does it come? Because we are writing the rate constant for this kind of reaction. This is Pa. Okay, Pa is equal to 2Pa minus Pt. So that can be written like this and totally we can write K is nothing but a 2.303 divided by T into log of Pt divided by 2 P1 minus P2 because Pa is nothing but a minus 2 P1 minus Pt. This is how, you know, we can easily obtain the rate equation for the gaseous phase of the reactant. Okay. So, hope you all understood. In the next class, again we are going to discuss with the half-life of a reaction And by this, I like to say that what are all the things which I covered in this session, especially the integrated rate equation for the first order and zero order, then significance, then coming into the rate constant for the gaseous phase reaction is also very important for the examination point of view. Have a look on it and try to work out. Wherever you are not understanding, pause the video and please practice it. Okay. We'll meet you in the next session. Till that, take care and be safe. Thank you.